make the decision trees as chaotic as possible, and they don't even waste their time checking if they've branched on that before. Now, in the case of categorical values, so for example, if your choices are match and mismatch, or no and yes, or t-shirt, none, and button-up, if you've already branched on something before, branching on it again is going to do absolutely nothing, right? So it is kind of a waste of time to branch on it again, and if you were to keep a record of that, your tree might actually build a little faster. But there's probably the simplest solution here is when you're building the tree, after you pick an attribute and a value to split on, you're going to have to do the splitting. So you take your data and divide it into two matrices. And if you find that all of your data is in one matrix and there's nothing in the other one, you have to do something about that case, right? You're going to have to handle that case anyway, because it could happen that you just happen to pick the very worst possible place to split on. Well, let me draw an example. Suppose here are the red points and here are the blue points, and you happen to pick this one, and you split right there. If you do that, or if you pick this point and you decided to split right there, if you do that, then obviously this is worthless because all the data goes on one side, and the question arises, what color do you color this region of the space? Do you see how that's kind of an unanswerable question? There's really no right color for this side to be because you have 0 data points on this side of the line. So essentially you can't let that happen. If you cut the data and there's no data on the other side, you're going to have to just pick again. Therefore, that already solves the problem. You see how that answers the question? So as long as you have to have this code anyway that says, if I didn't do any good, try again, then you don't really need to do anything else. So you can keep track of attributes if you want for efficiency's sake. It's probably better code, lots of stuff, but it's good enough to just kind of let it play out.
And then for categorical data, whenever we branch, like we need to know the values in which to branch on, but how do we, I mean, without keeping a separate list of all possible values for each possible feature, how do we know how to branch?
Okay. So let's look at my web page go. That's how I lost it. AI schedule. Assignment 6. Okay. Right here in this little bit of code I provide, I say class interior node extends node, and there's 2 values here, one for the attribute and one for the pivot. Okay. Attribute, my comment says which attribute to divide on, and pivot says which value to divide on. So the idea is, if this is continuous, I know that wasn't your question, I'm getting to it. If it's continuous, then pivot will be the value where everything goes left or right of it. So it's either less than or greater than. If it's categorical, if this attribute is categorical, then pivot will be one of the values that it can support. For example, if we were at this node in a tree, the value might be button up, because a shirt can either be button up, none, or t-shirt in this data set. Okay. Assuming the value is button up, then what I would do is I would divide that tree into only 2 branches. This tree actually branches 3 ways. You don't have to do that. And all the values that have shirt equals button up would go on one side of the branch. I guess that would be node A. And all of these samples where the value is something other than button up would go in branch B. So all of the nuns and the t-shirts would all go down branch B, and then they could branch again on the same attribute to split those two if they wanted. Did I answer your question?
Well, the question is, how do we know, like, I know the R format tells us what all possible values are for each feature, but how do we,
Excuse me.
I mean, I could sit down long enough and whiteboard myself to figure it out if you don't want to give the answer, but
Mhm.
how would I know exactly? Like, let's say, okay, I pick shirt, let's say there's three options. How do I know what those three options are without going all the way back into the R file, looking at feature and determining what the possible values are? Because then I could enumerate them, but I don't want to have to hard code the enumeration.
Yeah, okay. So if you find yourself writing some kind of a parser, you're doing work I never intended and you shouldn't have to do that.
Yeah.
So, yeah.
Or
So,
just need to pick a row and just pick that, and that's what I'm going to branch on, whatever that value is for that row.
okay, let me show you my matrix class. This matrix class is supposed to have done all the work for you of parsing all the information in the R file and presenting it to you in a way that's ready to go. So that should be the case. These are the member variables of the matrix class, and the main one you care about is data. So m_data is an array list of double arrays. And this is basically all of the values. It's just a whole bunch of numbers, and this is what you think of as this is what you think of as a matrix being, is that stuff. All of these are what I'll call metadata. So these values contain, this is the file name of the matrix. I don't even know why that's there, it just is. I actually didn't write this file. This was written by another student who wrote pretty nice code, and I asked if I could use his code. So for whatever reason, he thought the file name should be in there, so it is. m_attr_name, this is an array list of strings. Basically, this gives you the names of every column in your matrix. If you look at your data set, every column has a name, and this contains that name. As far as your decision tree goes, both of these are worthless because decision trees don't respond to the name of the column or the file name, so that's useless information. These last two are kind of meaningful. Stir to enum and enum to stir. Basically, this maps between, if you have a categorical value, this will map between its enumerated index and the corresponding string. So if we were, in this case, the shirt column would have values of 0, 1, and 2, where 0 would represent t-shirt, 1 would represent none, and 2 would represent button-up. And these mappings map from strings to integers and integers back to strings. So that's all you need to get there. However, I don't think you'll even need to do any of that in your decision tree, because your decision tree doesn't really care what you're splitting on. It just cares whether it's categorical or continuous. That's kind of all you need to know. So finally, let me answer that last question. How do you tell if an attribute, a particular column, is a categorical type or a continuous type? There's something called value count. There it is. Value count returns the number of values associated with the specified attribute or column. 0 is continuous, 2 is binary, 3 is trinary, etc. So essentially, here's what you're going to do. You pick a random attribute, which means one of the columns in your data set. Then you're going to call value count to find out, is it continuous or is it categorical? If it returns 0, it's continuous. If it returns any other number, it's categorical. If it's categorical, this will return the number of values in that categorical attribute. So, for example, the shirt attribute has 3 possible values, t-shirt, none, and button-up. So it would return the number 3.
So then you can just pick random in between 1 and 3 and use that as your branch.
Yeah, it's as simple as that. So
Okay.
at that point, you'll pick a random number, 0, 1, or 2.
Okay.
And whichever one of those it picks, that's the attribute you're going to fork on. And if it's continuous, then you'll pick a random value and then use its value. Let me take back what I just said.
No.
There's a better way than picking a random number from 0 to the number of values minus 1. The better way is take all of your remaining data, pick a random pattern from the remaining data, around a pattern in your row, and then look in that attribute and see what its value is. If you do that, that kind of implicitly keeps track of what you've already split on, because it'll be something that's in your data.
Right.
And that way you'll get something that makes sense to split on, and so hopefully it'll produce good values.
Okay.
That'll work for both continuous and categorical values, by the way. All right. Sorry for the very long-winded answer to a very simple question, but I had to both figure out what you meant and say a bunch of extra stuff that might be helpful. There we go. Okay. Another thing I want to point out, I think I mentioned this last time, but just to make sure, because this matrix class has a bunch of metadata stuff here, it's kind of important when you make a new matrix and then you move data from one matrix into the other, you'll lose all of this metadata if you aren't somewhat careful to keep it around. And do you see why you need to keep this data around? Well, the attribute values function, the attribute value function depends on it, so you need to keep it around at least just so that that thing can work. So in order to do that, there is this copy metadata function, which just copies the metadata from one matrix and puts it in another matrix. Hopefully that makes it really easy for you. There might be other ways to do it. I think there's a copy constructor in here. Oh, there is. There's a copy constructor, so if you want to do it the expensive way, you could copy the whole matrix and then throw out the rows you don't plan to use. There's probably other ways you can do it too. So I think you'll find everything you actually need is here in that matrix class, and it's not too bad to dig through. And if you don't, it's not that hard to work with matrices. Just write 2 for loops that runs through it and copies the stuff you need. Okay. Clear enough on how do you work with matrices? Has anybody coded it up and encountered any difficulties so far? Yes, tell us about it.
Something is weird. I think it's because the soy value or the soy data is all categorical. There are no continuous values.
Okay.
So mine goes into an infinite loop trying to split them up. And I think it may be because I suspect, I'm checking it now, that
Okay.
there is at least two entries that have the same categorical values all across.
Ah, okay.
I'm having a similar problem like that.
I would not be
Infinitely.
surprised at all if that is the case. There may be 2 rows that are just identical. And that happens a lot in real data sets, so this is a great experience in real world coding and all that kind of thing. But
Count the number of tries you've done. Once you go over that number, then you say, I'm just gonna make a leaf out of it, right?
that's exactly my solution. I would just make it timeout. So I would try maybe 10 times. I wouldn't try any more than that. If after 10 random draws you can't find something to split on that produces 2 matrices that both contain more than 0 elements, then I would just say, to heck with it, make a leaf node, call it good. If you do that, then your code at least will be robust, and it's better for your code to work than to go into an infinite loop, obviously.
So in theory, what I would do is, before I actually start building the tree, is check for duplicate rows.
Okay.
But how would
And then just
I?
throw them out.
Well, if they're completely duplicate in label and attributes, then you could throw one of them out. But how would you handle a case where they're different in label, but they have the same features?
Ah, okay. So technically, you should include both of them in the evaluation. Hopefully there's an odd number. suppose you have 3 of them, and 2 of them have one label, 1 of them has the other label. When you end up evaluating them, the more common label should prevail. If they're continuous labels, then you do some kind of an average. So they average the values together. If they're categorical values, then you count the number of occurrences in each category, and the larger number should prevail. Unfortunately, that gets to be a really big pain to code up. So I understand that as a pain, and that's why I'm actually recommending you just go with the try 10 times and then bail approach. It sounds like a hack, but truth be told, the only case where it even occurs is once you get way down to these leaves and you're in this rare case where there are these 2 collisions. And because we're doing random forest, we're building hundreds of trees and they're all voting, those little cases actually don't really even matter at all. So the way you handle it's just not going to make a big difference. I guess if you were doing a really robust tree, after 10 tries, then you could start getting all systematic by measuring how much separation there is between every attribute and find the one that gives you the greatest separation or something like that. For the sake of completion, I should show you how decision trees are classically built. So let's bring this up again. There is something called, well, has anybody ever heard of Shannon's information theory?
Yes.
Okay, so Shannon is a very famous guy, wrote a book about information theory. He's considered the father of information theory. Can't even remember his first name right now. It's not coming to me. Anybody know it?
Claude.
It's probably Claude. That sounds right. So, in fact, there was I just happened to come across a news article, I think I saw it today, where somebody claimed that Claude Shannon had built a personal computer, and this wasn't previously known. And I think they're debating about whether this is the oldest actual building of a personal computer. So, anyway, suppose we have some data points like this. There's a few different ways we can separate these. Obviously that's the best, right? Because that separates all the red from all the blue. But we could also separate it like that, or like that, or like that, or like that. And these are less effective separations. And we know that intuitively. How would you determine that mathematically? Just suppose I threw this at you and said, okay, give me some number that represents how good the separation is.
You could say the proportion
What's the goodness of that separation?
2/3.
Yeah, okay. So 2 is the number over here and 3 is the number down there?
What about?
Well then, how would that, clearly this is good and this is bad. This one would be 2/3. What number would you give this one?
I see what you mean.
See, there's this concept of color and there's this concept of quantity. And so I'm asking you to somehow
Maybe you could do a
generate some
ratio-
magic that evaluates this.
A ratio of, if you split it somehow, how much of the side contains red and how much side contains blue.
Yeah.
So this ratio would be 1:1.
Okay, there you go. So
100% red, 100% blue.
100%. So now we're saying 1-to-1 is the best possible case.
Yeah.
And then the worst possible case would be something like that.
1-to-0.
What would this be?
Or,
No, that'd be 200.
Two.
Well,
yeah,
Undefined.
what about the first one?
2-to-0.
What if you had like a percentage of correctly sorted, like in the first one, say 4/5, because you had 4 correctly sorted and 1, shall we say, not.
Okay.
And in this case, you have 0 correctly sorted.
What's correct? Maybe I'm supposed to have red on this side and blue on the other side. So I got 3 out of 5 correct on this side and 0 out of 0 correct on this side.
But where is that defined?
Exactly, that's my question. Where is that defined? Or how, when it comes time to coding it up, you encounter the trouble of, how do I code this up again? Is kind of what I'm saying. Okay, well, Shannon came up with this concept of entropy. Have you ever heard that the entropy of the universe is expanding? Essentially, that has something to do with the second law of thermodynamics. Apparently, the world's getting hotter. Lots of interesting things. Nevertheless, in information theory, entropy refers to a slightly different concept. Here's what it is. So Shannon was working with the idea of compression. And we're asking the question, suppose that I'm going to tell you what color of balls I've got in my data. And I'm going to, or dots, and I'm going to tell you either red or blue. Now, if you were to code this up, you'd probably use binary, right? 1 for blue, 0 for red, and then I'm going to say 1, 0, 0, 0, 1 as these are drawn, right? Okay, well that's all good, but what if, in fact, my data looked more like this? Now how would you code that up? Meaning, I want you to send a signal over the wire telling me what color I'm giving you, and I'm usually going to give you red, but sometimes I might give you blue.
The lazy way would be just iterate over the picture and then read what color the pixel is.
Perhaps. I think I'm not communicating the problem.
Maybe you could have a flag for blue, but
Yeah, so the problem is it's harder to get smaller than a bit, right?
Yeah.
And yet it seems kind of wasteful that the sequence I'm going to send you is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1. And so we spend a whole lot of time saying 0, even though you pretty much knew a 0 was coming. And what the point here is this isn't a very compact way of coding this up. So if what was coming over the line ends up being something like that, this data is definitely not compressed. There's a lot of repeating values here, and you could somehow encode those repeating values, but you can't quite get rid of that one bit, so how can we do it reliably? I can't remember exactly how Shannon says to code this up. Dang it all. There's some solution to it, and I can't remember what it is. However, that doesn't get away from my whole point, which is entropy. What's happening here is this is a case of not a lot of entropy. And the way we can tell there's not a lot of entropy in this data is because it's mostly the same, right? Whereas data with a lot of entropy is all very different. And how well we can compress it, even though I can't seem to remember how to compress it, the how well we compress it depends on the entropy of the data. Do you follow what I'm saying? If it's all 50-50, there's nothing better you can do than a 1 and a 0 to differentiate what's coming next. But if you have one of these cases, you can actually do this a lot less than just with binary. Okay, so the way we measure entropy is entropy. Let's see if Wikipedia gives us the formula. It's negative p times the log of p. Give me the formula. This is the wrong kind of entropy. I want information entropy. There we go. Entropy and information theory. Guarantee you we're going to see Shannon's name here. There we go. 2 Shannons of entropy. Okay. And there's the equation. Negative sum of p of x times log base p of x. How many red dots are there here? I think there's 21. I might have miscounted. And how many blue dots? So there are 2? Okay, thank you. So we've got 21 red, 2 blue. Suppose I ask the question, how much entropy is there here? The answer is -2 log of 2 plus -21 log of 21. Where this is log base 2 because we're doing information theory here. And whatever number that happens to be, let's figure it out. -2 times natural log of 2 divided by natural log
I
of
thought you
2.
said you were doing this in base two.
I am.
Oh, okay.
Change the base.
And natural log of 21 divided by natural log of 2. I divided by the natural log here to change the base because my calculator doesn't have an easier way to do that. -94. Doesn't sound right to me.
Me neither.
Oh, look, I got the same.
You got the same number? Okay. That's because I was supposed to do ratios, not actual quantities. I know why the number's wrong. Okay. Turns out 2 out of 23 of them are blue, and 21 out of 23 are red. The equation for entropy here is going to be -2 out of 23 times the log base 2, 2 out of 23, minus 1 out of 23 times log base 2, 21 out of 23. That's correct. Anybody done the math yet? That's correct. Okay. Okay, well, here you go. Behold a number, and that number tells how much entropy is in this system. Aren't you excited? Yay, we just measured entropy. Why did we measure entropy? Well, entropy tells us something. It tells us how not homogeneous this data is. Do you see how that's useful for decision trees? Well, we come back to our problem, wherever it may be. Here's a problem. Suppose we pick a split. Here's the split. We can measure the entropy before and after we split our data, right? Before we split our data, there were 1, 2, 3, 4, 5, 6 reds, and 1, 2, 3, 4, 5, 6 blues. That's really heterogeneous data. So before, that was really bad. After the split, 3 out of 4 are blue. So we're going to get less entropy over here. And over here, 3, 4, 5 out of 8 are red. So there's less entropy over here. And if we average those two together, we get that on average now, the entropy is greatly reduced, whereas before there was a lot of entropy. Do you see that? So what Shannon's information theory does is it provides a metric which we can use to evaluate how good is this split. And if we wanted, we could pick another split, like that one, and we could measure how much it reduces the entropy, and then we could just try all possible splits, or we could just pick a bunch of splits for a while. But the point is, we could, if we wanted to, evaluate how good or bad that split is. And that's kind of useful. So for years and years and years, everybody believed this is the right way to build decision trees. Is what you do is you try a bunch of splits and you measure exactly how much you are gaining by making that split. And if it reduces entropy by a lot, that's generally good. And they very, very carefully chose every division in their decision trees, and they built exactly one decision tree, and that one decision tree would end up being really good. So this is how decision trees were made for years, and it worked really well, meaning it made good decision trees, much better than the random trees you guys are building. Well, then along comes something called ensemble theory. In ensembles, instead of training just a single learning algorithm, you train a whole bunch of learning algorithms, and you let them all kind of vote. And they all work together to try to build a better classifier. And they tried that with decision trees, and they found out that it worked really, really well. Then they tried it with random trees and they found out it worked even better. And then people started to realize, hey, all this entropy stuff and all this theory behind evaluating the divisions of our trees are actually a lot of work, and why even do it? So now they don't do that anymore. And that's essentially what it comes down to. So if you start digging through this book that I've thrown at you, you'll see a whole bunch of things about, where is it? Choosing a division, entropy reducing trees. So in machine learning, entropy reducing trees are a really big deal, and there are a lot of good reasons to reduce the entropy of trees. For example, suppose you need a learning algorithm that's really, really, really fast. If you have just one decision tree, it's going to be way faster than if you have 100 decision trees, right? Okay, so if you need one decision tree that works really well, this is how you want to build your decision tree, is measure the quality of each split and make really good splits. If you have a really fast machine and you just don't care, build a random forest. For some reason, it does even better. And that's kind of where we're at. Okay. So I took this big tangent mostly just because I wanted you to be aware of what it was. I'm not going to ask you on a test, what is the equation for Shannon's entropy? You could look that up at any time. But I do think you should at least have got from what I just said, what is entropy? You should understand it's some measure of the homogeneity of data. And if I were to ask, how is that useful with decision trees, you should be able to explain that could be used to evaluate the quality of a potential split. Okay? So having said that, I don't think it's worth teaching anymore because random forest beats it. And that alone is enough valid reason to me to think that, hey, that's not the right thing to do anymore. So when you're building your trees, all we're going to do is pick a random attribute, pick a random value, split on it, recurse until we're done. Okay. Now that we've done that, I'm going to draw your decision tree like this. It's a binary tree. So every branch of your tree will contain 2 nodes. And your decision tree will look kind of like this. And inside each of these nodes, you'll have both an attribute that you have split upon, and a value that you split upon, right? Now, depending on the attribute, some attributes are continuous, some attributes are categorical, but the attribute number that you pick will tell you which one it is. You can look it up, and then you can check against the pivot value, or the value you've split on, and then decide whether you're supposed to go right or whether you're supposed to go left. And so this is a tree. Now the question comes up, how do we use the tree? Okay, so how do we use the tree? Let me show you, see where we can start here. Let's start all the way in our code. We'll work through that. In our supervised learner.java class, every learning algorithm has to have a predict method. In the predict method, you'll pass a vector, an array of doubles called in, an array of doubles called out. What are these? In represents the features, meaning the values that you want to classify. Out represents a blank space for you to write the answer. Does that make sense? So if we're doing the hepatitis problem, in will contain your temperature and your age and whether you have spots and whether you have spiders on your skin and all those attributes that you measure to determine whether they have hepatitis. Out will be a buffer of size 1, and you'll either write die or not gonna die there. In your case, it'll be 0 or 1. Okay? So if we come back to this picture, we have this vector of features in, and it arrives at this first node in the tree. Now what do we do?
See if it's a leaf or not.
Yeah, we'll check, are you a leaf? It's not. Now what do I do?
Get the dimension that splits on.
Yeah, I'll say,
and
okay,
check.
which attribute did you split on? By the way, I've been using the word attribute, dimension, column, all interchangeably. Are you lost or you caught that? Attribute, dimension, column, all the same thing to me. Do you prefer one of those words over the other? Good, they all mean the same thing. So, this node already represents some column in your data, and that's not going to change. So let's suppose it's column 3. So I'll take my attribute vector and I'll look in value 3, and I'll compare it with the pivot value here. And if it's less than, I go this way. If it's greater than, I go that way. Or if it's categorical, then I say if you're equal to, I go this way. If you're not equal to, you go that way. Or maybe the other way, depending on how you wrote your code. But I go the way that's intended. Okay, now I come down here. I say, are you a leaf? No. And then I compare the right column in my data with the column that it had stored in that leaf node. And then I go the way I'm supposed to. And I get here and I say, are you a leaf? He says, yes. So I take whatever label is stored in this leaf node and I copy it into my out vector. So getting back to the code, that's, I copy it to this place. And then I return, and now I have used my decision tree. Do you get how to use a decision tree? Okay. What's the code for that going to look like? Well, pretty simple. I'll say node n equals root, something like that, while not n dot is leaf. And then by the time I get here, I'll say vec dot copy into out whatever n dot label has. So essentially, I've just got a loop here that's going to run down my tree, and I just have to say if n dot is categorical, then do this. Else do that. And if it's categorical, then I'll say if in of n dot attribute, or attr is the attribute that I'm splitting on in node n, is less than n dot pivot, n equals n dot a, else n equals n dot b, something like that. Was that clear enough that you could follow? I don't think that will compile, but, and then, wait a minute, I did the real case in the categorical region. There. Now I did it for categorical. So if it's categorical, we're just checking whether we're the same thing as the pivot. And if we're continuous, we check if we're less than the pivot. That's about it. I think your code will look a lot like that, or at least something similar to that. Okay. All right, so that's a decision tree. What else is there to say about decision trees? I think you guys are now experts on decision trees.
In your book also, you said that, I guess there was one case where you limited the number of, you limited the depth of the tree. In the
Oh,
book,
yeah.
an example of script 4.
Okay. Yeah, so let's assume that you have some, okay, let's go back to this example. I use this one a lot, but here is some data. And remember how we were talking about how if we have a model that looks like that, there's a reasonable possibility that that's actually better than a model that hits every single data point, right? Because chances are good that a lot of this up and downiness is due to noise and not due to an actual pattern in the data. And if we're fitting things that aren't real patterns, that's what's called overfit. And that doesn't actually make us make better predictions, it causes us to make worse predictions. Well, the same thing happens with decision trees. When you have a whole lot of data points, and they tend to overlap a little bit, well, turns out that the best decision tree might just really be something simple like that. But if you keep on splitting until you get it exactly right, you often end up having weird cutouts that look like that inside of your model just to handle a single data point. Does that make sense? So this is what we call overfit, and it actually makes the decision trees a little bit worse. In order to ensure that we get good decision trees that aren't too unnecessarily complex, you can just stop going down so deep if you want to. A simple solution is, once you chop it down, if we say, hey look, there's only 3 data points left in this region, don't split anymore. Does that make sense? So it's really, really easy to code up. You just have some number and stick it in a member variable, and once you reach that number of patterns in your matrix, just call it quits, make a leaf node, stop splitting. If you do that, that often makes your trees work a little bit better. So I figure you should put that feature in too, just because it's super easy to code up. So I stuck that in the requirements. Okay?
And then how do you pick the most common label out of those points?
Yeah, it'd be the most common label. And in fact, in this starter kit that I gave you, there's code to find the most common label. So if you find yourself writing code to count the most common label, I already did it for you. What's that?
You said the student wrote the matrix.
Oh, yeah. I think I actually wrote the code to do that, though. It's in the baseline class. Look at the baseline class. It's only this many lines of code. You know, you should be able to handle that. I need a mute on this dumb thing. Every time I cough, that's going to be super loud on the video. Oh well.
Just normalize the volume.
Normalize the volume. Yeah, that'll do it. I don't think I even care that much. I'm not going to go watch these videos again. But I can't honestly imagine you guys are either. I mean, why would you do that to yourself? Okay.
Sometimes they are useful.
Okay. I guess maybe there's a possibility that there might be a test on this at some future point.
What?
Okay. Maybe. Okay. Next, let's talk about ensemble theory. There are a lot of learning algorithms. Let me mention some of them to you. So I'm going to talk about supervised learning algorithms. So the one you're writing right now is called the decision tree. There's another popular one called the neural network. That's the one I talk about a lot because this is my favorite model. And we use neural networks with the sumo billiards problem. So you're very familiar with them. There's a model called k-nearest neighbor. This is a very simple model, but it's pretty effective and pretty popular. There's one called naive Bayes. There's one called support vector machines. You ever heard of any of these learning algorithms? There are rule-based learners. There are, what else is there? There's a lot of them.
Why is that one called naive?
Because it's simplified.
So
things. It
there,
makes some assumptions.
yeah, there are much more sophisticated models, such as Bayesian graphical models. And it turns out that you can implement naive Bayes using Bayesian graphical models, but you can also use Bayesian graphical models to do things that people who study Bayesian statistics would call not stupid and more correct. And So Bayesian graphical models are a big topic in machine learning, but they're really hard to use and you have to have a lot of expertise. Naive Bayes makes a whole bunch of assumptions and turns out to be super easy to use, and it doesn't really make very good predictions. In fact, of all these models out there, it probably makes the worst predictions consistently. But it is blazing fast. Of all these models out there, Naive Bayes is by far the fastest. And so Naive Bayes is used often with places where you have crazy amounts of data. And when you have a lot of data, it actually starts to do pretty well, or comparably with other things. And so due to its amazing speed and robustness to big, big data, it ends up being a rather useful algorithm, despite the fact that it does some things that Bayesian statisticians would say are mathematically cheating.
Like it assumes independence a lot.
Yeah,
In
it
places
assumes
where-
independence in cases where it's definitely not independent, which is bad statistics. But then again, it just works, and it works well and really fast. So
It's just
it's
accuracy
not really.
trade-off for speed.
Yeah, it's accuracy for speed. And as it happens, when you have tons and tons of data, you often don't need the world's best learning algorithm. You need the world's fastest learning algorithm. And these learning algorithms do better the more data you have. So Naive Bayes isn't really a bad learning algorithm. It's just bad compared to these others when trained on the same data. Okay, Google is pretty much sold on neural networks these days. And when used properly, you can make neural networks really fast these days by parallelizing them and throwing lots of processing power at them, parallelizing them on GPUs and things like that. Neural networks are starting to make Naive Bayes look really stupid because when done properly, neural networks can be trained on almost anything Naive Bayes can as well. But there's a lot of caveats to that, and that's only partly true and not always entirely. So there's that. Having said all of this, one of the reasons I wanted to point to you that there are a lot of learning algorithms is, well, there's a lot of things to try, and suppose you have some problem, which learning algorithm is the best? Unfortunately, it depends on the problem. So for years, people kept trying to evaluate the learning algorithms to say, this one's better than that one, no, this one's better than that one, and people did all kinds of studies trying to figure out which learning algorithm is absolutely the best. Till a guy named David Wolpert finally did a proof, and he proved that it turns out that there exists a problem that's best for any algorithm. And it turns out that no matter what algorithm you come up with, there exists some problem that can beat it. And so there is no best algorithm depending on the problem, unless there is some set of problems that you know to be more important than others. If you consider all problems to be equally important, no learning algorithm is better than any other, which is an interesting thing. That kind of suggests that humans are no smarter than worms, doesn't it? Technically. Because worms can be just as smart as humans. Except that's only true if all problems are equally likely. And a funny thing about the real world is not all problems are equally likely. So for example, if I were to start spewing static electricity or something like that right now, that would just be weird, right? I mean, that's just not going to happen. But it's a possibility. And I don't know why a worm would be more equipped than a human to handle that. What I'm saying is, imagine that your life, imagine that you lived in a world where the information your eyes suddenly received was completely random. I mean, white noise in front of you constantly. Everything you heard suddenly became How would you deal with that? What would you do?
Kill myself.
You would be incapable of operating. You couldn't discern what's going on, and you could never learn from it because it's just too chaotic. This shows us that humans are effective because there is some order in the universe. There's some patterns. There are some problems more likely than others. Consequently, maybe there is a best learning algorithm because not all problems are equally likely. And the only way we can prove that learning algorithms aren't no learning algorithm is best is if we make the pathological assumption that all problems are equally likely. Okay, having gotten to that, can we use them all together to make a better learning algorithm? That would be cool, wouldn't it? So the idea comes, what if we just have them all vote? So suppose we take the hepatitis problem, we train a decision tree on it, we train a neural network on it, we train KNN on it, we train naive Bayes, a sort report vector machine, and a rule-based learner, and all these other things we can think of. And then we have them all vote, and the decision tree in the neural network says you're going to die, k-nearest neighbor says you're going to live, naive Bayes says you're going to die, support vector machines say you're going to die, and the rule-based learners say you're going to die. What do you think is going to happen? Probably going to die. Although it's possible that whichever one I said you were going to live actually knew better, and it just happened to be one of those cases where all the others don't, right? But usually you kind of feel like the one that votes the most is probably more likely to be right, don't you? Okay.
That sounds like it would kill any computer, just.
Yeah,
because it
that's the
requires so much
problem.
computation.
That's the biggest problem, is neural networks take a darn long time to train. These are probably the slowest algorithm of them all, unless you have it parallelized properly. In which case, suddenly, weirdly, they become the fastest when used properly, because they don't have a huge model. Now, some of these others are pretty fast. Naive Bayes is blazing fast. Support vector machines are pretty darn slow. And this one takes a lot of memory, and having a lot of memory is just about as bad as taking a long time. Suppose you want to train all of these things. It's going to take a long time, so which ones are you probably going to put in an ensemble? The fast ones, right? Decision trees are fast, naive Bayes are fast. Let's put those in an ensemble, have them vote. No, it won't kill your machine. So for a long time, people were training various models and sticking them in ensembles, and they found that yes, in fact, if you do that, it does slightly better than the best algorithms in there. So suppose neural networks are the best, and yet if you have them all vote, that's even better. Well, now we have to add another one to the list. So let's do all of them voting. And now if all of them voting takes the crown, then we have to do that one, right? But can all of them voting be ensembled with each of these? I don't know, that's a weird idea.
Ensemble of
But
ensembles.
an ensemble of ensembles. It could probably be done, but you're going to start running into computational limitations. Okay, well, one problem with this whole approach is the more learning algorithms we have voting, the better this ensemble is going to do. But it's a lot of work to come up with a new learning algorithm and to code it up. There's probably 200 of them out there in existence. The world's best learning toolkit probably has 80 of them implemented. And, well, what if you want 100? It's going to be hard to come up with new learning algorithms. So why not just stick one of them in there twice? What's that going to do?
It's kind of skewed.
Yeah, if you have some, you're basically giving them 2 votes if you stick them in there twice. Does that make it better or worse? I'm going to claim usually worse. Yeah, it depends on the problem. The thing is, that answer is always right, so you can just always be ready to say that, but it's not always helpful to say it, but it's always right.
What about a random ensemble then?
Yeah, so that's, I guess, what I'm building up to is we'd like a bunch of algorithms, but they have to be different. If you just give them 2 votes, that's not helpful. So it turns out that neural networks are really stable, and that's really bad because if we train a bunch of neural networks in different ways, they all end up being about the same anyway. And so it's just the same as if we stuck it in the ensemble twice. Decision trees, it turns out, are really, really unstable. Meaning if you slightly perturb the training data, then they make a completely different model that's very, very different from the model that you'd have if you didn't slightly perturb the training data. Well, that's usually bad. But in the case of ensembles, it turns out that that's a really good thing because what we can do is slightly perturb our training data and then train a bunch of different decision trees and throw them all in the same ensemble, and amazingly, they get better. And so that's what we're doing here. Okay. So let's talk about bootstrapping. This square represents your matrix of data. Every matrix has a bunch of rows, and every matrix has a bunch of columns. So there's a whole bunch of numbers filling up this square, and I'm not going to take the time to write them. Just understand that this square represents a matrix. You with me? Okay. Now if I draw a horizontal square spanning it, that represents a single row of data in this matrix. And I don't know how many rows there are, I'm just saying this is some row I picked at random. Okay? Now, the way we do bootstrapping is we allocate a new matrix of the same size as the original matrix that we have. So suppose this is your original data. I'm going to pick a random row from this matrix. I'm going to press Control-C, and then come over here and Control-V it over here, and paste it right there at the top of my matrix. Then I'll pick another random row from my matrix, copy it, and go paste it over here. I'll pick another random row, copy it, go paste it over here. You see what I'm doing is I'm reordering my matrix, right? But I might accidentally pick the same row twice, and now I've doubled up on that row. And then I might pick a different row and then paste it over here. And I might pick that same row again, and it might actually appear 3 times. That's kind of the stink, but it's actually okay. And if I do it again, by the time I'm done, as soon as this matrix is full of, pretend it's full. By the time this matrix is full of data, it's pretty much the same data as this data. It's just that it's been shuffled and reordered, and some of the rows appear twice. And if some of the rows appear twice, some of them must be missing, right? Okay. Well, this is called resampling with replacement. The with replacement means it's as if after you drew it and put it over here, you put it back. You replaced it in the original matrix, so you might draw it again. Now, when we sample with replacement, we create a matrix that is like the original matrix, but is a little bit different. That's it. Why might we do that? Well, if this is our training data, we can generate slightly different training data by doing this. And that's useful because if we then use a volatile learning algorithm such as decision trees, then we end up with a completely different model. So if we train 100 different decision trees using 100 different bootstrapped matrices, I lost track of which one it was. That one. So we generate 100 different bootstrap training data matrices. We train 100 different decision tree models. Now they're all basically different models. We can throw them all into the same ensemble, and now it produces a really highly accurate learning model, and that's what we call random forest. Oh, and one other thing. Take away entropy reduction and make random decisions, and now the decision trees are even more volatile, and now it works even better. Okay? So that's random forest, and when you write random forest, you'll have to write a resampling with replacement snip of code. Can you handle that? It's really easy. Okay. How about the voting aspect? How are you going to implement voting?
Have an array that can store results from each decision tree, and then just count how much each one says you're going to live and how many say you're going to die.
Yep, that'll do it. And in fact, if you look at the baseline algorithm, that's how it aggregates all of its labels into a single label. So in fact, you can just do the same thing. So this is actually no different from what you do in the leaf nodes or from what you do in the baseline algorithm. It's just that same code again. Is just take that code and it computes the average of continuous values and the most common value of categorical values. And that's basically what you'll do here. So after all your trees vote, use that baseline approach to find the most common value that they predict, and that's what you now predict. And so now your random forest can do that too. Okay. Now, by the way, this is one ensemble technique. This ensemble technique is called bagging. It stands for bootstrap aggregating. Where bootstrapping refers to this process of resampling your data, and aggregating refers to the process of voting. And when you put them together, it becomes bagging, and it turns out that bagging ensembles of random trees, which is called the random forest algorithm, is really effective at making predictions. Okay. Any other questions before I turn you off to go code this up? Because I think I think you've got the theory, I think you've got the implementation details. Random fire rest. Hey, there's a bug. I should fix that sometime.
I like the virus class. Would we please name it that?
Sure. It turns out that the random forest is actually trademarked by, I think Bremen is the guy that probably trademarked it. And so it's technically illegal for me to use the term random forest without his permission. So maybe I better leave it just to stay out of hot water. I'm not being very serious. I don't think he would even care, but. Did we argue for what?
For like fair use.
Oh yes, that's the real reason I'm not being very serious. Is if he tried to stand up against that, I'd just say fair use, and then I'd stick the U of A lawyers on him. And, I mean, that's kind of silly to prosecute a professor for using a name. But they do make a lot of money off that brand name. It's a very popular brand name these days, I believe. Okay. Cool. Let's talk about some other ensemble types. Just because we can. So, actually, I'm starting to wonder if I'm piling too much on you. If I start talking about other ensemble types, is that going to cause problems? Or yes.
Also, my laptop just died.
The laptop just died. All right. We only got 10 minutes left. Want to just call that it?
Yeah.
I think I'm done. My voice is worn out. Thanks for coming. Go code it up. Use your extra 10 minutes to get jumping on the assignment. And if you have trouble, do post on the forum. I'd love to help solve your problems.
Column size stays the same every time, right? Even though we're splitting on columns, and we don't keep track of, hey, we split on this column. It doesn't matter because we might